Our objective is to be able to find the radius and interval of convergence for a power series. Well, it sort of makes sense for us to flesh out a definition of what a power series exactly is. Let's start there. So power series, we've already saw a simple example back in the warm-up exercise when we were taking the sum, the infinite sum of x to the n. N is the index for that series. So this would go, if I started with 1, it'd be x plus x squared plus x cubed, and so on. Okay, but if we define a function based on this, where x gets to change as well, then I get to stick in something for x. And the only thing that I really care about are all those values that I can stick in for x, for which that series would converge. So in other words, let's say that I stick in -1 for x. Then my series becomes a summation of just -1 to the nth. It looks like this. So it's 1 minus 1 plus 1 minus 1 and so on, which doesn't converge, it oscillates, so we say that that diverges. What does that mean? That means I'm going to take the number -1 and it is not part of the domain of this series. Get rid of it. All right, so maybe I try something else. Maybe I try -1/2. So if I plug in a -1/2 here, then it's -1/2 raised to the nth power. This is a geometric series where the absolute value of that common ratio is less than 1, so it's in good shape. It converges. Specifically, it converges to 2/3. So I get to use -1/2. And notice that whenever we stick in -1/2 here, it's just a regular series, specifically a geometric series. So I could graph this. I could graph this as a function where my input is -1/2 and my output here is 1/3, right? And then maybe I try to see what else could work in here as something that would converge. How about, let's say, 0? Well, if I plug in 0, I'm just summing up a whole bunch of zeros. Now, one thing that I am going to mention here, I think this one actually starts at an index of n equals 0. And really, this first term here is 0 raised to the 0 power. In terms of series, something, or 0 raised to a 0 power, is going to be taken to be the number 1 instead of that indeterminate form that we talked about way back with L'Hopital's rule. All right, so this means that 0 is good to go. So you would have the point for your function 0, 0 if you plotted that as a graph. All right, and then what else? How about +1/2? Sure, +1/2 happens. That's what we showed back on the warm-up exercise. And so 1/2 would be plotted together with its entire sum of 2. And then maybe I choose another one. How about the number +1? So +1, this time you just get a whole bunch of ones. That's going to go off to infinity, so it diverges. So it's out of the running. So again, what a power series is, you can think of it as just a collection of series. It's all the series for which, like whatever it is that I can stick in here that make this a convergent series, right? And we're going to define a function based on here. So here is the formal definition of a power series. If x is a variable, then a power series is an infinite series of the form, and here's what it looks like. And now notice that this one is maybe just a little bit more complicated than the one that we were looking at before. We have the infinite sum from n equals 0 to infinity, and then we have a sub n that's being multiplied times this x to the nth. Now realize that n is the index for this summation, so it's the thing that gets to count up. So starting with 0, x to the 0 power is just 1, and then you would have the very first coefficient here. All right, and then whenever I increase the index to 1, it's x to the first power, which you can see here, and it's the first coefficient, and so on. We just add up all of those things. This a sub n, those are all the coefficients for our variable x. And that in itself could also be a series, as we're going to see in just a second. So maybe here's some examples. We have the infinite series. We have 1 over n is our coefficient here that's being multiplied times x to the n. And so this 1 over n as the series, that's just the harmonic series, right? So this one would probably have to start with 1 instead of 0 because you don't want a 0 down here at the bottom. And then maybe this one just alternates here. And then this one has 1 over n factorial that's being multiplied times each one. And then again, what we want to know is what are the values of x that make this each one of these things converge when we throw away all of the rest of those things. Okay, so for each power of x, the power series becomes a series of constants which may or may not converge. Whenever I stick in, say, the number 1 or stick in the number 2, does that make a series that converges? If it does, it's part of the domain, this thing that we call the interval of convergence, and if it doesn't, then we throw it away. Okay, so specifically, this is a power series centered at 0. But we can center it any place that we want to. Let's say, for example, at C, where C is some sort of constant. So it's going to look exactly the same. It's just, doesn't this look sort of like what we did with the Taylor series? And so this, or Taylor polynomial, this one over here would be like the Maclaurin one, where it's centered at 0. And here, the Taylor one, which is centered at any other number C. So let me give you some examples. This one here would be centered at 1. And here, this one is another one that's centered at 0. And then this one centered at a -1. All right, but again, what the whole entire point is to try to determine what are the values of x that makes this a convergent series. And that is a thing that we're going to call the interval of convergence. Okay, so again, we're going to take this and turn it into a function. We take all the values of x for which the power series converges. We're going to define that as a function, and a function has inputs versus outputs. The input is the number that you're going to get to stick in for x to turn it into a series that converges, and the output is going to be the sum of that series. So here is the function now. So you can see that it's exactly the same power series that we saw before, but now the input for the function is a number that we get to stick in here for x. Maybe it's the number 1. The original one that we looked at before, the number 1, was not part of the domain, so we would throw it away, but the number 1/2 was, -1/2 was, 0 was, and so on. It just depends on the particular power function that we're looking at here. Okay, so the domain, again, is just the set of all values of x that you get to stick in for x that make this a convergent series. The range is just going to be the sum for each one of those values of x. If I stick in 1, then what's the sum of that series? When I stick in 2, what's the sum of that series? And then you could plot this thing as a graph. I wonder what the thing looks like, right? All right, now the domain for this power series function is called the interval of convergence. And it's what this whole entire lesson is all about, is trying to figure out what the domain of that function is, which is something that you started to do way back in Algebra 1. You continued in Algebra 2 and in Pre-Cal. Hey, what's the domain of this function? It's something that we care about. It's just that this one's special. We call it the interval of convergence. It is all the values of x that make this function, this power series, a convergent series. Okay, and at the very least, it says it's always going to contain its center point. And that center point can be 0 or this value of c. So here's an example of this. This one is centered at c, as you can see. If we plug in c here, then all of these terms right here are going to cancel out because it's c minus c. Those things are all 0. And you're just left with the first term. So an interval of convergence is going to take on one of 3 forms. The first form is shown to you right here. It contains its center point. That's the saddest case of all. But hopefully it contains some kind of interval that we can get. Maybe it's, say, from -1 to +1. And then the last one is that we're going to see is it contains all real numbers, which is really nice. Okay, so here is that note, same one that I alluded to earlier in this lesson, that when we take 0 raised to the 0 power for series, we're just going to understand or accept that that is the number 1 instead of having to use, say, L'Hopital's rule on it. Okay, so in the next lesson, or the next video, I should say, we're going to get down and try to discover how it is that we come up with this interval of convergence for a given power series.